and thank you very much for joining today's Energy Storage News webinar. We will be starting promptly in 2 minutes' time, as scheduled. So if you need to make last minute, I don't know, get yourself a glass of water, pen and paper, anything you need to be comfortable and give the speakers your full and undivided attention. You have about 1.5 minutes to do that, and we'll see you very shortly. Thank you very much. Hello everyone, and welcome to today's Energy Storage News webinar with CSA Group on large-scale fire testing requirements for battery storage systems. My name is Andy Colthorpe. I'm the editor of Energy Storage News and Deputy Editor-in-Chief for publishing at Solar Media. In this session, our expert speakers will cover an emerging aspect of fire safety, which is absolutely essential to the success of scaling energy storage deployment to the levels that the world needs. And that need is unequivocally clear. This year at the United Nations COP29 climate talks, governments are being urged to sign a pledge to get the world's installed energy storage capacity to 1.5 terawatts by 2030, which represents a 6-fold increase from where it stands today. Without that, it simply will not be possible to triple global renewable energy capacity to 11.2 terawatts by that time, which again is what is needed to be on track to limit average temperature increases to within 1.5 degrees Celsius of pre-industrial levels and avert the very worst impacts of climate catastrophes that many parts of the world are sadly already experiencing. But let's say we do get an agreement to support that rapid growth of energy storage. What then? How does the world achieve that goal? Well, according to the Coalition for Action, overseen by the International Renewable Energy Agency, or IRENA, implementing national energy storage targets and regular assessments of electricity system flexibility would be a major step towards it. IRENA's Coalition for Action comprises 150 non-governmental stakeholder organizations, and in a new series of reports, it includes those national storage targets and flexibility assessments among more than a dozen recommended measures to support and enable the 1.5 terawatts by 2030 goal. Now, politicians and their advisors set policy targets, and the industry can only hope that they will do the right thing and we continue to advocate for them. However, much of the future direction of the energy transition is also in the industry's hands. The IRENA Coalition for Action's preliminary findings, published last week, emphasize the critical role of industry standards and certifications and related compliance in the safe deployment and operation of renewable energy and energy storage technologies. So, to quote from those preliminary findings, although many standards have already been introduced, existing mandatory safety-related standards for battery storage are insufficient. At system level, many norms still follow voluntary principles and are not formally established. Fortunately, leading players in the industry are continuously introducing and improving best practices around safety and standards, such as the US National Fire Protection Association's NFPA 855 are helping to guide their widespread adoption. Large-scale fire testing is an important part of that, and today's expert speakers are about to tell you why and how it can become a standardized piece of the industry jigsaw. Today's speakers are Michael Becker, Global Business Director for Energy and Power at Standards and Certification Specialist CSA Group, and joining Mike is Christopher Groves, Product Manager at Wärtsilä Energy Storage and Optimisation. As always, interaction with you, the audience, is really important to us. And the speaker presentations from Mike and Chris will be followed by a Q&A session with the audience, which I will moderate. Please put your questions for the speakers in the questions tab that you can see on the right-hand side of your screen. Now, we will try and tackle as many of those as we can, but we can't promise to be able to get through all of them. But rest assured that CSA Group and Wärtsilä will be more than happy to reach out to you afterwards and continue those conversations offline and answer your questions in full. Finally, today's session is being recorded, and the video recording will be available to view on demand from the Energy Storage News website in the coming days. So I think that's about all from me for now. So without further ado, it's my great pleasure to hand over to our first speaker, Michael Becker. Over to you, Mike.
All right, thanks, Andy, for that introduction. So as mentioned at the introduction, we're going to be talking about large-scale fire testing for energy storage systems. So a quick introduction into myself and also Chris, who I'm being joined by. As Andy mentioned, I'm the Global Business Director for Energy and Power at CSA Group. I have experience in the compliance and engineering and new product development fields for energy storage systems, batteries used for motive power and backup applications as well. And I'm joined today by Christopher Groves, who's a product manager for Wärtsilä Energy Storage and Optimisation. He's responsible for the fire and safety compliance for Wärtsilä's quantum battery energy storage system product portfolio. He's also focused on maintaining Wärtsilä's reputation as a leading BESS integrator with the highest safety record of any integrator on the market today. And both Chris and I actually participate in the standards development process for applicable energy storage system standards such as UL 9540 and NFPA 855. So this is an agenda of what we'll cover during my section of the presentation before I hand it off to Chris. And so let's get into it by considering our first topic of the purpose of large-scale fire testing. So why is fire safety so important for commercial and industrial energy storage systems? Well, as you can see by some of the numbers on this slide, energy storage systems are increasing the deployments and installations at an exponential rate. And the reason for this, as Andy mentioned at the outset, is the switch over to clean energy sources that could be intermittent, and also the fact that everything is becoming electrified, from home appliances to electric vehicles. And so this electrification puts a huge amount of stress on the utility's ability to provide clean and reliable power. And the deployment of these systems are really happening globally in many regions. The one example I have here is the United States market. For example, energy storage deployments were up 86% from 2023 to 2024, with about 10.5 gigawatt hours of capacity installed. Now, if you think about an average of around 3 megawatt hours per 20-foot container, and that is going up, of course, that's around 3,500 20-foot shipping containers installed in just one quarter in one country. So it helps us to appreciate the how much and how prevalent this is becoming. If you add on top of that the average price for batteries have decreased about 34% in the same time, it further improves the financial viability of these systems. Now, the potential fire risk really comes from the fact that most of these installations make use of lithium-ion batteries due to their cost competitiveness, their energy density, efficiency, and cycle life, just to name a few benefits. But as many of us know, lithium-ion batteries experience a rapid heating condition called thermal runaway. That could be caused by manufacturing defects, environmental conditions, or other stresses. Now, the amount of energy and the speed at which the energy is released during a fire for a battery is usually much higher than other traditional energy sources, like a generator. Also, as you see pictured here, many of these installations have multiple containers installed next to each other, pretty close to each other. And so the picture shows what could happen with an energy storage system at a site where we have a fire experience in one container and there's other containers around it. So the question is then, how is this being addressed by current standards and testing? So many of us probably are familiar with the main battery fire testing standard that has been used for the past several years, and that is UL 9540A. Now, this has been considered kind of the go-to testing methodology for fire testing for cell, module, and unit level. A typical setup I have pictured on this slide is where you have a central initiating unit where thermal runaway is induced, and then you have target units around the initiating unit to determine heat exposure. Now, how does this testing perform? Well, usually a battery cell or multiple cells are forced into thermal runaway using a specific method, typically a thin film heater that gets put on the side of the cell. Now, the only requirement in this procedure is that some type of cell-to-cell propagation needs to happen. But does this accurately capture the fire safety risk of large-scale installations? Well, although the cells might be forced into thermal runaway, the gases that come off of the cell may not be ignited, and a result of the test could be that no fire condition was achieved at all. And so that type of result, no fire condition, would be considered an acceptable result per UL 9540A. However, just having cells venting gases but not having a fire may not simulate real-world conditions of a fire in a system, which leaves uncertainties about how a fire might spread if it does happen in these large-scale installations. In a real-world scenario, these cell gases could be ignited by many different sources, and so this is a current gap with the testing standard. So this brings us to our purpose of large-scale fire testing. Now, kind of put simply, the purpose of large-scale fire testing is to intentionally ignite a fire within a single energy storage system unit, fully involved fire, and then see how it might spread to nearby systems or the nearby environment. As we considered, this is really critical for utility installations that have multiple energy storage system units installed next to each other. It really answers that question. If one ESS is on fire, will it jump or spread to the units next to it? Another purpose of large-scale fire testing is to gather data that's necessary for risk assessments. And Chris will touch on that in his presentation as well. And so this data can help AHJs and first responders understand what to expect if one of these ESS units are on fire. How should they respond to a fire? Can they just let it burn? Will it release toxic gases into the nearby environment? What will the surrounding environment be exposed to if there is a fire? And so these are all questions that are answered through this type of test. We actually have pictured here a real setup that we performed on one of these units, and that Chris will touch on later with the Wärtsilä testing. Okay, so let's transition from the purpose of testing to the testing methodology and setup. How is this test performed? What is this test? Well, as we consider, the first step is to cause a forcible ignition of a fire in a single enclosure with the goal of whether it spreads to adjacent units. And so the single initiating unit, the one kind of in the center, is typically populated with battery modules, as would be in a real-world scenario. Target units are then located around the initiating unit with the spacing and separation that would be in a real installation. Now, these target units could be populated with real battery modules or dummy modules to represent what would happen to these adjacent systems. Now, many different initiation methods can be used. We've used a lot of different ones in the past, depending on the design of the system. But one default initiation method I have pictured here is typically a combination of large heater pads on the modules to cause cell venting, a thermal runaway, in combination with some type of external ignition source, sparker, or a propane torch burner as pictured here to ignite the cell gases. And so that's just one example of how we would actually perform this test and start that fire condition. Now, what type of data do we collect during this test? That's usually a question I get. Well, the main determination made for this test is whether a fire will spread to the units next to the initiating unit on fire. So that's the first observation we make from this test. Now, the way that we make that observation is based on the data that we capture through videos, pictures, thermal imaging of the test, heat flux gauges, temperature measurements, internal cameras. And so all of those measurements that we make, along with the videography and the photography that we're doing during a test, gives us a complete picture of what's happening on both the initiating unit and also the target units around the main unit. Now, we also make a lot of other measurements during this test that help answer other questions from stakeholders. We also make measurements on the surrounding environment, whether it be through heat flux gauges or instrumented walls, to provide information on what would the egress points look like, a surrounding environment. And so this also helps first responders and fire departments understand what to expect during one of these fires. Now, in addition, as you can see pictured here, we do collect the gases coming off of this test. We can actually pull these gases off of this ventilation hood and do some complex gas analysis that gets analyzed through a complex series of instruments. So these measurements include flammable gases produced, smoke density, heat release rates, but we even also measure the various toxic gas that might be exposed to during a test, or even any other type of gas constituents. And so pictured here is actually our state-of-the-art facility in the US where we do this testing. Okay. So now I'll briefly touch on CSA Group's experience in large-scale fire testing. Now, although the term large-scale fire testing might be relatively new to some on this call or others in the industry, CSA Group has really been involved in large-scale fire testing for over 2 years now. We not only perform one of the first large-scale fire tests, but we also keep testing bigger and bigger systems, testing so far up to a 40-foot shipping container. We've performed probably over 15 large-scale fire tests. That number has probably gone up, and it goes up every month. And our fire testing capabilities expand beyond just large-scale fire testing. We do perform the standard UL 9540A tests at our Cleveland, Ohio facility, which is pictured on the top of this slide. And we also have a facility now that we just opened out of China that also does the 9540A testing. Pictured on the bottom here is actually our command center, where you would observe a test for large-scale fire testing, where you're able to monitor the test live and kind of see everything that's going on during a test. The one thing that CSA we really prided ourselves on with this approach is our consensus approach to standards and product safety. We realize the importance that all stakeholders play in product safety, not just us, but there are a lot of others in the industry that have a lot of experience in design, testing, and approvals of these type of systems. And so we worked really hard to gather the input from stakeholders in the ESS industry, as mentioned here, AHJs, insurance providers, manufacturers, EPCs, in involving them in our process with this testing. We've invited these stakeholders to tour our lab facility, involve them in our standards development process, and also have them review our report that comes out of this testing to understand, are they seeing everything that they want to see in those reports? Is there anything else they would like to see? Other data that we should be collecting? And so this type of interaction with stakeholders really helps improve our service, what we're offering, but it also is a benefit to ones who are performing the test because they're doing so in a way that the industry wants to see. Okay, so I got a couple minutes left. I'll just touch on a little bit the standards development work that we're doing for large-scale fire testing. Now, many of you have probably heard of the CSA C800. As we talked about earlier in the presentation, there's a gap with current testing standards with fire testing. And so we really needed a documented test procedure that could be repeated in a way that captures what the stakeholders in the industry want to see. And so being one of the only testing companies who have performed this test repeatedly and having a standards development organization as part of us, we were really positioned well to work with our colleagues in the standards department to start development of this standard. And so in answer to that, we started development on CSA C800, which is actually now out and is out for public commenting. So I have the link here, and Andy will share it later as well. It's out for public commenting until, I believe, December 3rd. So we invite, again, in the spirit of transparency, we invite everyone to take a look at it and even provide comments if you want to have some input into that standard. And so the main point is really that this will be the first consensus US, Canadian, ANSI approved standard that would capture, along with other testing requirements, large-scale fire testing. Many of the stakeholders I mentioned before were involved in the development of this standard, and so we included their input as well. Now, what we did in the meantime, because the challenge we were facing is that we were asked to be doing this test now. We were being asked by AHJs and manufacturers to do this test, but as you know, it takes time for a consensus standard to be released. And so what we did in the meantime is we released CSA TS 800, which is a technical specification. So this is basically an interim document that you can use for performing large-scale fire testing. Now, this document wasn't created by CSA by ourselves in a vacuum where we just came up with this. This was actually the direct work from the task group that was part of CSA C800 that created this procedure. And so basically we just provide it to the industry, the output from that task group before the consensus standard comes out, just so that the industry can start to benefit from the work that we've already done and the experience that we have in this testing. Now, once CSA C800 is released, then TS 800 would kind of go away and just be absorbed into the consensus standard. And then my last slide before I hand it over to Chris is just some high-level codes and standards development updates. As many of you know, large-scale fire testing is being clarified and included in many of the latest fire codes, like NFP 855, the CFC, and the IFC. We'll continue to emphasize the CSA C800 as being a large-scale fire testing, having that methodology in there as being an important part of this. And many of those code updates, large-scale fire testing is becoming mandatory, will become mandatory for many types of systems. This is what is being asked for. So even though we're doing it for a few AHJs right now, it's only going to be continually adopted and referenced. And so we see that picking up. And so CSA Group will remain at the forefront of this testing, our standards development, and help to facilitate safer ESS installations with the help of our stakeholders that we work with. All right, now I'll turn it over to Chris Groves, who will touch on it from the manufacturing side.
Thank you, Michael. Again, my name is Chris Groves. I represent Wärtsilä Energy Storage, Inc. We'll talk about this large-scale fire testing requirements and how it relates to BESS systems. So at Wärtsilä, our #1 commitment is to ensure that our energy solutions are built and installed with safety at the forefront. So Wärtsilä has worked with industry leaders like CSA and successfully executed 4 large-scale fire tests to address the growing concerns around fire safety. So the purpose of these tests are really to, from a manufacturing standpoint, validate our heat flux modeling, support client permitting, including community risk assessments, provide accurate emergency response plans to improve response tactics, and prioritize education of customers, first responders, and communities. Let's look at validation of modeling. Large-scale fire testing data is used for creation or validation of site-specific heat flux analysis, including but not limited to unit-to-unit spacing, row-to-row spacing, distance to oil-filled equipment, distance to adjacent structures or property lines, and these should factor in site-specific wind speeds not replicable during testing. So you can see some images on the right. The one on the top left is a flaming event inside of a single cube and its impact to the adjacent cubes beside it. The image on the right is a flaming event inside a larger cube and its impact to a unit across the aisle, considering a 30-mile-an-hour wind speed. So capturing this data during the large-scale fire testing will validate or invalidate what may be modeled for that site. A community risk assessment evaluates the potential for toxic gas, flammable gas, heat, and overpressure extents and any impact to the site, the fire service, or the public. Plume models should be at a minimum based on 9540A module level results or unit level. But large-scale fire testing provides the most accurate information for these plume models. This data is instrumental in addressing appropriate setback distances from property lines and minimum approach distances. You can see here on the images on the right, the first image is the thermal radiation level for a fireball scenario and its impact to adjacent equipment. On the bottom is the vapor cloud extent for a particular site and its impact from that releasing unit. This information is valuable in ensuring that the community and the surrounding area takes into account what these release scenarios may be. Emergency response plans. Large-scale fire testing results are imperative to ensure the emergency response plan accurately reflects real failure scenarios and is supported by the results of the large-scale fire testing. Examples include, are the exclusion zones accurate? Does the large-scale fire testing support a let-it-burn approach? How long do subsystems remain active? Will the fire service still be able to monitor the BMS and adjacent enclosures? What is considered an escalating event and how to know when that is happening? And how long is the fire service expected to remain on site? So does the system burn for 2 hours, 8 hours, longer durations? This information is valuable for them to understand and plan appropriately. Then we look at education. You need to address the gap between manufacturers and stakeholders. So you need to ensure that your testing aligns with appropriate industry best practices, like this TS 800 standard, and addresses the AHJ's concern. Maintain a fire safety first mindset, regardless of where the project scope is, what the contract language entails, or where the site lives. We discuss with our clients the importance of creating a community risk assessment and providing emergency response plans to relevant stakeholders. We take a project-specific approach, factoring the fire safety, the site layout, human and environmental conditions. We encourage early and frequent discussions between manufacturers, AHJs, developers, and insurers. And we ensure you are working with manufacturers who maintain safety as a top priority. So no two manufacturers are the same. What are some things to look out when you're evaluating a best supplier's large-scale fire testing results? Were the systems installed at a minimum distance outlined in the product manual? Does that reflect in your site layout? Was the initiating method appropriate to ensure propagation leading to a worst-case fire event? Were all racks engaged during the test? If not, were the racks engaged representative of the worst-case exposure to adjacent units? Were any of the critical safety systems operational and monitored during the testing? Was plume data collected during the testing that can be used for a community risk assessment? And what does their safety record look like? And do these large-scale fire test results reflect actual events that have happened in the past? With that, I'll turn it back over to Andy for questioning.
That's great. Thanks very much, Chris, and thanks a lot, Mike. Yeah, really quite a quick presentation, but very, very information packed, and rich in insights from both of you. So thanks very much for those. I can see the audience appreciates it a lot too, with lots and lots of questions coming in. So yeah, we'll turn over to the Q&A session now. So sorry, bear with me, little technical problem there. So just a couple of key messages that I'd like to get across before we go into that Q&A session. So there is a battery energy storage system BESS fire safety forum upcoming. So CSA Group is holding an exclusive event called BESS Fire Safety Forum, February 26th, 2025, at their lab in North Carolina in the US. Now, this event will bring together leading fire safety experts, regulators, insurance representatives, and energy storage industry leaders. Highlights include an engaging panel discussion on ESS fire safety, a tour of CSA Group's large-scale fire testing lab with a live demonstration, and of course, valuable networking opportunities. Attendees to this webinar will receive an official invitation via email soon. And one other thing, if I can get the link to work. So the fire test, the large-scale fire test procedure that CSA, sorry, I forgot the name of it. There's TS800, the large-scale fire test procedure. So gonna put this on the screen as a link that you can click now. And if you're reviewing the video afterwards, then rewind back to where Mike put the link up on the screen as well. So during today's webinar, Mike introduced the CSA TS800:24, and that addresses a critical gap in fire safety by providing a standardized method for assessing fire hazards in energy storage systems. Now, this technical specification is open for public comment until the 2nd of December. So you have a couple of weeks to get involved there. CSA Group encourages everyone to review the draft and submit feedback to help shape a standard that best meets industry needs. Now, in the unlikely event you somehow basically can't click the link or something, or you just miss it, and I'm about to take it off the screen, so you might miss it. You can also actually Google CSA TS800 large-scale fire test procedure draft public comment, and that should bring it up for you there. Okay, so hope you've all clicked that, and we are going to go into audience questions. And lots of questions have come in, which is great. As I mentioned, we are not going to be able to get through all of these, even though actually the speedy presentation means that we'll get through maybe a few more than we usually would, which is also good. But CSA Group will be more than happy to follow up and continue these conversations in full offline with the folks that ask the questions, and presumably CSA Group will also pass that on to Wärtsilä as well for any specific inquiries that might go Wärtsilä's way. All right, so guys, you ready for your questions? And the first one comes in from, try and go easy on you at first, but like a large scale fire test, kind of have to put everything through its paces, don't we? So we'll see how we get on. So Ben, thank you very much for your question. Ben asks, once contracted and equipment is ready, how long does the process of full large-scale fire testing typically take?
Yeah, I can take that one. So I think typically, once we have the samples on site, we usually budget at least 3 to 4 weeks of setup and testing and teardown for the actual testing itself, and usually around 4 to 6 weeks at each end for test planning, which happens at the beginning, and then also the reporting, which happens at the end. So I would say around 3 to 4 months. Best case if we have samples and everything's available to do the large scale fire test.
Okay, and we had kind of a couple of other questions around this as well. So Ben, you're going to get 2 questions answered because you put 2 in the in the same sentence. So does CSA Group anticipate its testing procedure becoming a consensus standard or influencing consensus standard at some point in the future? I guess that's another one for you, Mike.
Yeah, that's a good question. So I guess I'll start quickly with the fire code, because in the end, the code itself is what'll dictate what gets adopted or what gets referenced, right? So NFP 855, I would say, is kind of the overarching the highest level of code, and so there will be language in there to require large scale fire testing, and there is even information on what that methodology should look like. But there's not a reference to a consensus standard because there is no consensus standard right now. So that's how the next the 855 code will look. The TS 800 basically mirrors what's in that 855 material. So it's kind of just a method that is very aligned with that. The goal would be that C800 becomes a consensus standard pretty short term in the next few months. And then we would be able to use that as a reference for an actual consensus standard. So it's kind of it's still, I think, up in the air which consensus standard will end up being adopted into a code. But for now, the code will require large-scale fire testing. We just provided a way that people can do it repeatedly.
Okay, great. And so in terms of the tests, Tyson asked, so thanks for your question, Tyson. And I think you kind of did maybe go into this a little bit in your presentation there, Mike and Chris, but maybe just a little bit more color and detail on this would be nice. Like, what actually counts as fire condition? Does off-gassing without flaming fire pre-thermal runaway count? Does thermal runaway without flames count as well?
Yeah, I'll start that one, and Chris, if you want to add to it. Basically, there needs to be visible fire or coming from the battery modules themselves. So just venting would not be considered large-scale fire testing. Even if there's thermal runaway but no flame, that would not be a large-scale fire test either. So that's why we have the external ignition sources, to make sure that even if the only result is venting or is just gas, we actually purposely will ignite those gases to start the fire.
Chris, any perspectives on that? Oh, you're on mute there.
Yeah, I'll agree with Mike. The NFP 855 2026 version referencing large-scale fire testing does indeed see that there should be intentional ignition of vent gases to understand the fire behavior.
Cool. Okay. And yeah, I mean, it's a lot of questions. Let me sift through these. So, going to ask 2 in one because these again are quite closely related questions. So, Ankit and William, thank you very much for your questions. So Ankit is asking, with the intentional ignition of a BESS enclosure on one rack or rack, would the fire suppression system be allowed to operate? And similarly, William asks, for large-scale fire testing, should testing be carried out with or without fire mitigation measures such as fire suppression systems installed? So the fire suppression equipment, is that kind of off limits during the test, or is that something that's also kind of put through as part of the test?
Do you want to take that, Chris, or?
I'll let you answer, then I can.
Okay. Okay. So if I remember correctly, So basically, in the 855, the new material, basically the idea is that the fire suppression in the initiating container doesn't impact our ability to achieve a fire condition. So we wouldn't start the test, ignite, and then initiate a fire suppression that then reduces the event. So that's not the intent behind it. The intent is to have a fully involved fire of an initiating unit. Now there is some text in there that allows some mitigation scenarios to be put in the target units. So the ones around the initiating unit, because in a real world scenario, worst case scenario, the initiating unit is up in fire. The expectation would be that your target units still have their protection systems engaged and active. And so those would be typically allowed to be maintained there. So that's kind of the framework behind it. What we've been doing is working a lot with the AHJs very closely, and I'm sure Chris, does this as well from the manufacturer side to understand what they want to see, right? Because the code is not out yet. It's not released. So right now, it's really up to each AHJ individually what they want to see. And so it would be the responsibility of the developer, the EPC, the manufacturer to understand that, because they may say, I don't want to see any fire suppression, or yeah, it's okay, you can do it. So right now, that's kind of the way that we're approaching it. I don't know if Chris, you have anything else to add?
No, I agree. I think this really is, to clarify, this is a fire test. It should show propagation, and there should not be any, say, active system to mitigate the fire during this testing. I will clarify that this is not an explosion system test. It's a fire test. So there may be separate standards in the future that are testing the effectiveness of, say, an NFPA 69 or 68 system. This test considers that those systems either are active or potentially have failed, and we're only looking at a fire scenario.
Excellent, thanks. And lots more questions on the actual testing, testing procedure and standards itself. But I think one question around, let's say, evolving industry best practices in kind of fire mitigation or risk mitigation. So thanks for this question, Bruno. So in a recent battery storage fire safety seminar by another system integrator, they stated that their policy was to let it burn and mitigate propagation to other units. Is that industry opinion as well? Now, from my kind of less educated than Mike and Chris's viewpoint from the industry, just from what I look at across articles, kind of do see that a lot of folks are sort of introducing, kind of seeing let it burn, as long as, things are restricted to one unit being kind of the main thing. But I may well be wrong on that. So why don't I let the experts speak on that? Chris?
Yeah, I think from an industry standpoint, this is really what this large-scale testing is looking at. So in a reasonably worst-case scenario, when you have a fully involved unit, does it support a let-it-burn approach if you can demonstrate you do not have propagation to an adjacent unit? Now, this does not take into account, say, excessive winds or a potential scenario where there may be another exposure concern near the units. So again, it's going to end up being site specific, and the ERP should address in these incidents, maybe you need to apply cooling water to the adjacent units if there's very high winds and a flame tilt onto the adjacent unit.
Great, and we did have a couple of questions around ERPs or emergency response plans, right? So yeah, we'll see if we have time to get onto those, because that's a little bit more of another aspect of industry best practice. But Mike, I guess from let's say from the view of someone that isn't a system integrator, any view on let it burn, or is that more, I guess that's less around the sort of testing standards itself? But yeah, do you have a view on that?
Yeah, I mean, I think, like Chris mentioned, that's kind of the whole purpose of why this test exists, I think, or one big driver behind it. So that's, in our discussions with the stakeholders, that's kind of what they're looking to see, is if there is a fire condition, can they let it burn, right? Can that be the approach that they take? And so this test would be a big piece of that. So I think that's a question that's asked a lot. So I guess I would say yes, it's probably a common industry approach or viewpoint. And then it would be up to each manufacturer to do their ERP for the site-specific considerations, like Chris mentioned.
Okay, great. And kind of back on the test specifically, Stephen's question. Thanks for your question, Stephen. Are there pass-fail criteria prescribed for the heat and or temperatures and off-gassing both in and outside the units during this large-scale fire testing? So is there sort of like a pass-fail criteria in terms of heat or in terms of temperatures? Heat and temperatures, kind of the same thing, aren't they? And off-gassing, yeah.
So yes, again, so if we think about kind of the setup that I had pictured in my slide and the purpose behind it. So one of the pass-fail criteria is, do you have propagation in those adjacent containers? So if you actually have live battery modules in those containers around the one that's on fire, do they enter thermal runaway? So that would be a pass-fail consideration. The other one that is also called out in the NFPA guidance is, some manufacturers, they don't want to have to put fully populated containers around an initiating container, because these systems can be very expensive. So the other pass-fail has been, if the temperature on module housings go above the venting temperature that was captured in the 9540A cell test, then that would also be, you would basically say that would have entered thermal runaway. So that's also, I didn't get it too much in depth, but that's also one of the considerations of, do you populate or not populate target units? And we get that question a lot. And usually it's just a determination of how much risk you want to take on. If you don't have it there, you're doing more of a temperature measurement that could be impacted by more transitory increases, or do you have actual modules there? And it makes it really clear, would you have propagation or not? So that's the main, I guess I would say, pass-fail. Everything else is a lot of just data collection.
Awesome. And Chris, I don't know if you've got a perspective on this specifically, but I wrote a story this week about the most recent third and fourth large-scale fire tests that you guys carried out with CSA Group. So I don't know if you have any observations to note with regard to those particular tests, and how that kind of sits in with what Mike was saying about the way that the fire tests essentially evaluate the overall safety performance of the system.
Yeah, I mean, during our testing, we are looking to address these AHJ concerns. So is the distance from unit to unit appropriate? When do subsystems become active? When do they become deactive? What fails when and why? And really, in a passive approach, no suppression, full-scale fire, is the distance appropriate? From a performance perspective, I think it's very subjective. It's really a learning tool for the entire industry. What happens in these scenarios? From our side, we try to target, do the temperatures in adjacent units reach cell venting temperatures, or is there a risk of it escalating? And we were successful in demonstrating during our testing, we did not reach cell venting temperatures.
Okay, awesome. And, I think, as you alluded to at the very beginning when you guys ran through your bios, you're both in a position of providing some input towards the NFPA 855 standards, I believe. And yeah, I'd love to maybe hear a little bit more about that. But Jonathan asks, so thanks for your question, Jonathan. What changes do you see coming out in the new revision of NFPA 855 around NFPA 68 and 69? I'm not sure how much you can reveal in terms of discussions that you've been privy to. Perhaps it's more about kind of the principles around updates and changes. But yeah, we'd love to have some color on that. And maybe if you want to add anything about kind of the work that you guys have been doing in there and what that entails, that would be super interesting as well. So I don't know who wants to take that first, but would love to hear from both of you if you have a view on that.
I can discuss it. So at least the NFP 855/2026 draft, it actually strikes out in the explosion chapter, allowing both NFPA 69 or NFPA 68. So NFPA 68 has been struck out as being a option for explosion control. So this system must be maintained, tested, and operated with the 69 system. This can be supplemented with the NFPA 68 solution, but a partial volume deflagration evaluation should be conducted in accordance with NFPA 68.
Awesome. And Mike, anything on that?
I don't think anything specific other than what Chris mentioned. I mean, as far as the overall changes, there's a high volume of modifications and edits that will be happening. So I think the second draft report is still being worked on. I didn't see it last time I checked, which will have a lot of the comments and results from those comments out from the last meeting that happened. But main thing we were focusing on is large scale fire testing, but there are a lot of other changes that I would suggest people kind of keep up to date and keep on the lookout for on the next revision.
Sure. And sorry, I think you might have just mentioned it then, but when did you say the next revision is likely to go public with the draft?
I think it'll be the 2026 version. I believe it would be next year. I think it would be released usually during the annual conference is when they do the vote on it, if I'm not mistaken.
Okay. Awesome. And so Adam was asking, so thanks for your question, Adam. Again, maybe something for you, Mike, but also maybe if Chris has a perspective on it from an end user perspective. So Adam asks, what are some of the specific gaps in existing fire testing standards that CSA C800 helps fill? And yeah, I mean, I guess you did allude to a couple of these during your presentation, Mike, but again, any more detail you can give for Adam there?
Yeah, I mean, I think the main thing, if I would break it down to the main issue, is just intentional ignition of the gases. So I think that's the main gap that we're addressing, because existing testing standards, you can just have, as mentioned in the first question, you can just have venting, you can just have thermal runaway with gas release, and that's okay. There's no that's an okay result for the testing that's existing. And so, the response from a lot of the stakeholders and AHJs is, well, that's not enough for us. We want to see what happens if it's on fire. So really the addition is actual ignition of those gases. So that's the main thing that we're addressing through our standard.
Awesome. And Chris, anything from a sort of end user perspective looking in towards that?
Sorry, I was trying to reply.
So
Ryan's in the chat. What was the question?
No problem. Yeah, no problem. So gaps in current standards that CS800 potentially can fill, I guess.
Yeah, I mean, if you look at 9540A, you're looking at, a single cell being heated into thermal runaway and showing, how does that propagate within the module to other modules. This new testing standard really is a true fire test, a reasonably worst case condition that really is, what we see in the field. Say last year, there were a number of fires in the industry. So this test really is used to demonstrate and fill that gap. When you do have propagation, what can be expected? So we applaud CSA in working and releasing this draft standard and working with them to help develop it as well.
Awesome. And somewhat related to that, Roger asks, how do you define a worst case fire event, and gives the example of a single cell into cascading runaway, internal short, external short, resulting in multiple cell runaway. I mean, is there a definition you can really have on a worst case scenario?
Yeah, I think the one thing I guess I'll note is the way that the procedure is written. I don't want to say it doesn't matter how it happens, But there's a lot of different things that can happen to actually cause a fully involved fire of an ESS unit. And so our goal is not to define how that is supposed to, how that would happen in the field, because it's hard to predict all the different ways it could happen. So our goal is to just create a fully involved fire condition, which could be from many different things, and to see, to characterize the fire safety from that type of test. So that's kind of the way I think we're looking at it. I'm not sure if Chris, you have another thought on it, but that we're kind of looking at it where whatever happened, it's on fire. There's a fire condition, and how do we, what's the performance? Does it spread? Things like that.
Yeah, I agree with you, Michael. So we're looking at a fully developed fire that's self-sustaining, and ideally has propagated from one rack to at least one additional rack.
Yeah.
Great. Awesome. And I think this is quite an interesting industry question from Jim. So thank you very much for your question, Jim. So I wonder if Jim asks, have you tested any of the latest DC blocks with 5 to 6 megawatt hours of energy storage capacity? So, we see the energy density going up rapidly of containerized systems. I'm not sure what you can reveal publicly about any of those, because perhaps people will be able to figure out which products you're talking about. But essentially, are there observable differences, I guess, is the point, with these much higher energy density systems that are now on the market, if that's a fair question to put to you in a public forum?
Yeah, I think that's probably tough to answer. I wouldn't want to broadly characterize, the difference between them. We have, like I said, we're kind of at the forefront of this test. At least, we do testing constantly at our US lab. So I would say, we've tested a lot of systems even recently, if that answers that question. But as far as characterizing the difference, I don't know if I would. There's a lot of different things that are changing other than just energy density, right? Like there's a lot of other parts of the system that end up being updated and changed that could impact this test. So it's kind of hard to do an A to B, just say higher energy density means worse test. But we're seeing a lot of different energy densities, a lot of different layouts, a lot of different spacings, a lot of different designs, and so all of them kind of have their unique approach and what could happen. And so each manufacturer is very different in how they do these designs, and so it's hard to compare one to the other if it being the same.
Awesome. Okay. And we go from these fire testing and standards, and then clearly what happens there should be positively influencing kind of what happens in the factory and in the field and in integration. So Francis's question, I think, is an interesting one, asks, how does data from large-scale BESS fire testing influence the design and operational effectiveness of fire suppression systems, especially in terms of agent selection, deployment speed, and coverage? And I don't know if we want to maybe broaden that out to, obviously fire suppression systems are a really important part of it, but just system design in general. But yeah, this sounds like it's maybe one for you, Chris, and then possibly if Michael has anything to add.
Yeah, at least from our side, from a manufacturer, we say fire suppression systems, we are not a proponent for. We would allow a dry pipe or water suppression system if mandated by the AHJ, but it's not something we actively have standard in our product. So ideally, this test is used to demonstrate you can have a let it burn approach and not have propagation to adjacent units. So from our side, we're really not taking this data. It's not a, say, 9548 installation level test where we're testing a suppression system and its effectiveness. That would be a more appropriate standard compared to large scale fire testing. But in general, water is the best cooling method for BESS systems.
Yeah, I was going to mention probably the same thing, like if you're measuring detectiveness or effectiveness of fire suppression, it's really 9540 installation level is that test. This is, as we mentioned earlier, this test is kind of despite the fire suppression, because you're in an already fire, sustaining fire condition. And so by this point, it's usually pretty late in the design process. Maybe some are different, but usually by this point you have the design, and the only thing it kind of informs is what appropriate size or separation distances that you need between units. But I don't know how much it would. It could impact the design of the system if you have intense propagation between racks, possibly. But really, it's the separation between containers.
Okay, brilliant. Thanks very much, folks. I think we're going to do one final question, I think, and then unfortunately we're going to have to call time for today. But it's been a brilliant discussion, and literally dozens of questions coming in. So everyone who's asked a question, don't worry that if your question didn't get responded to. As I said, the speakers and their respective organizations will be able to reach out to everyone that asked a question, and basically continue responding and continue that conversation at leisure, really, I guess, and in the fullness of time. But I think an interesting one to finish on, which again I think speaks to the let's say the link between the industry and being honest with society, really, I guess. So the installation of battery storage systems, I think community engagement is becoming a much bigger part of, well, renewable energy industry in general, but for battery storage, I think safety is a big part of that. So David asks, and thanks for your question, David, does Wärtsilä provide third-party engineering reports or other analysis to support developers to work with AHJs to understand the application of NFPA 855 based on large-scale fire test results and reports? And there was another question as well, if I may, and I forgot who asked it, but it was a question around formulating emergency response plans with first responders. So, Chris, I wonder if this is one for you. Obviously, the first part is for you, but so maybe specifically the application of NFPA 855 and whether Wärtsilä provides kind of third-party engineering reports or other analysis around that. But just in general, I think it would be good to know like what type of education work that you think needs to happen, or engagement work that you think needs to happen with AHJs and with first responders to kind of ensure not only the safety, but that like communities can have a certain degree of peace of mind around battery storage systems.
Yeah, to answer the first question, yes, we do provide third-party analysis and documentation in line with NFPA 855. So at Wärtsilä, we provide a hazard mitigation analysis, we provide heat flux analysis, NFPA 69 or 68 analysis, a generic community risk assessment. All of this documentation we prepare can be made site-specific, either through Wärtsilä or by a third party. And we also provide emergency response plans, both the construction, operation, and first responder emergency response plans that, again, can be made site-specific, and training provided for developers and first responders. That was the answer to your second question. Your first question. Your second question, I think, was related to how do we get the education out there. So it's really, obviously this webinar is one of the key ways we can get this information out. Other avenues, Michael, myself, we go to these industry trade shows, events, and I think, Andy, you mentioned there's one coming up that CSA is hosting at their lab in North Carolina. So this is really where we can take these lessons learned. If manufacturers are willing to share information, or these nerdos like CSA can, what is going on in the industry? What are we seeing? How is the codes developing? These are great avenues where you guys in the audience can get additional education on these latest and greatest offerings and changes in the codes.
That's right. Yeah. So the as you just mentioned there, Chris, CSA Group's Best Fire Safety Forum. That's 26th of February, 2025 at CSA Group's lab in North Carolina, including a large-scale fire testing lab tour with a live demonstration, panel discussions on ESS fire safety, and of course, valuable networking opportunities. And one final plug for the link there on the screen is your opportunity to offer public comment into the CSA TS800:24 large-scale fire test procedure. That's open until the 2nd of December, and everyone is encouraged to review the draft, submit feedback to help shape a standard that best meets industry needs. So with that, yeah, I just want to say it has been a really lively forum today and a great discussion with the audience, and certainly some terrific presentations, which I think help bring that, towards to everyone's top of mind, really, I guess you could say. So, Mike, Chris, it's been a real pleasure working with you both, and yeah, thank you so much for your time and valuable insight. And most of all, we want to say from all of us, thank you so much to the audience. Thank you for your valuable time. I want to say that the best time to deploy renewable energy was yesterday, but the next best time is now. And yeah, it's a terrific industry that you're all a part of. And yeah, please keep on keeping on, I guess, as some people say. So yeah, that's all from us today. Thank you very much, and goodbye for now.